All right, let's talk about the notes that you should have written down that are concerning polar molecules. All right. The one thing to look at the idea of polar molecules is think of the idea. What do you know that has poles on it? And maybe something, if you can think about it, think of the Earth. And the Earth has a North Pole and a South Pole. All right, and then if I want to figure out where the North Pole is, I hold on to a compass. And the little needle thing that spins around will like point towards the north. Now, do you know why it pulls towards the north? Well, because it has a magnetic pole. And that little needle is attracted to the magnetism of the North Pole, and it points towards the north all the time. Right? So when we talk about polar molecules, we're going to be talking about molecules that have a magnetic pole, very similar to the Earth that has a magnetic pole. Right? But again, we're talking about little bitty molecules rather than the humongous Earth. Okay? So, in regards to polar molecules, the first thing we're going to talk about is non-polar. So in the notes there it says non-polar. So non-polar means it doesn't have these magnetic poles. So I'm going to diagram one. We're going to diagram nitrogen. Nitrogen is diatomic, so it's N2. Let me switch to black. I think black shows up better. So we got N2. So in doing N2, what I have is I end up with, there's 5 electrons around him. So there's 5 for him. And then I take my second one and put 5 around him. So there's his 5. So I have a single covalent bond. If I look at the circle here, this guy's got 6. And this guy has 6. Well, that's not enough. So I'll bring this guy over, bring this guy over. Now I circle this and I got 7. And I circle these and I got 7. So that's still not enough. So I bring this one over, bring this one over. Oh, now I have 8 and I have 8. So there's my final thing. So now when we look at these 3 pairs of electrons that are being shared in the middle, excuse me, it's a triple covalent bond. How are they being shared? Right? Because these guys are basically going around this one, and they're going around this one, they're going around this one if you want something to visualize. Well, does either of those nitrogens have more of a pull on those electrons? Well, nope. Actually, they both have the same pull on the electrons. So we could really say these electrons go like this, and then like this, and then like this, and they're sitting here going this way. And who are those electrons around more? Neither one. They're actually around both of the nitrogens equally. So because they're around both of the nitrogens equally, then we don't end up with a pole. We don't end up with a magnetic pole like the North Pole and South Pole of the Earth. Right? So that's what it says inside your notes is electrons are shared evenly between the 2 electrons. Now remember, this is being shared, so these are covalent bonds. So we're able to take covalent bonds and make them into 2 different things, and one of them is going to be a non-polar molecule. And later on we're going to get to a polar molecule. So covalent bonds actually have 2 subcategories, polar and non-polar. Right, so how do we know if this thing is going to end up doing this? Well, what we can actually look at is we can look at a property that scientists have measured, and it's a thing called electronegativities. It's nothing that you have to like come up with or anything like that. All you have to do is you just look up a chart that gives you the electronegativities for each element on the periodic table. Right? And all it would be is you can go on your phone, look up electronegativities, and you'll get a big old list of all the elements, and it'll tell you their electronegativities. And then what you have to do is you go, okay, well, what's the electronegativity of nitrogen? What's the electronegativity of this nitrogen? Well, it's going to be the same. And electronegativity, by definition, is their want for electrons. How badly do they want them? And scientists have given them a number to be able to tell. Well, both of these numbers are going to be the same. So they both want the electrons equally. So neither one of them pulls them more, so they sit there and they're shared evenly between them. Right? Now, if we look at the periodic table, without even looking at a chart of electronegativities, if we look at the periodic table, actually the way that elements are arranged in the periodic table shows us their electronegativities. The most electronegative element is this guy right here, fluorine, in the upper, what would that be, right-hand corner. Sorry, I'm looking at it backwards on the screen. So the upper right-hand corner, he's got the most electronegative. He wants electrons like crazy, right? And he wants to pull them in. Now, who is the least electronegative? Way down here, francium or cesium, either one of those guys. Usually we look at cesium. Francium's electronegative, so, or I'm sorry, he's radioactive, so we don't really play around with him a whole lot. So So cesium, but basically this corner down here, least electronegative. And what we find is as we go across the periodic table and go up, they become more and more electronegative, right? So now if two elements are right next to each other, like fluorine and oxygen or chlorine and sulfur, then they're going to have really, really close to the same electronegativities. So therefore, they're going to be similar to this thing back here, and they're going to be a non-polar molecule. But if we're looking at something like fluorine and, let's say, sodium going together, their electronegativity is going to be really different, which is going to lead to the one later, which is going to be a polar molecule. So we can actually, again, another way of looking at this periodic table, and if you remember at the beginning of the year, I told you by the time we got done, which we're almost done, you're going to be able to say there's a lot of information that we can pull off of this periodic table. And this is just another piece of information, is electronegativities, and tells us how these molecules, these atoms are going to go together and make molecules. All right, so going through the notes there, it says equal electronegativities. The nitrogens back here have equal electronegativities. By definition, that's an atom's want for electrons. That's the definition of electronegativities. Fluorine is the most electronegative. Cesium is the least electronegative. So then it says for number 4, note where these elements are in the periodic table. And we can again use the periodic table to compare electronegativities of two elements. The closer they are together, the closer their electronegativities. The farther they are away from each other in the periodic table, the more different their electronegativities are going to be. And especially as we go down and over, or if we go up and down, the farther they are away, the more electronegative difference there's going to be. Number 5, there's no partial charges on the two elements. This will make more sense when we get to the end of these notes, but these guys don't have any partial charges. Examples of nonpolar molecules, things where it's the same two elements. Nitrogen, 2 nitrogens. Hydrogen is H2, that would be 2 hydrogens bonded together. They're both the same electronegativity. Oxygen, they'd both be oxygens, same electronegativities. Oil is nonpolar, which I gotta look at it and go, why is that? Well, oil is made out of carbon with some hydrogen and oxygen around the outside. So it's really carbon bonded to carbon. Well, it's just the same two elements. So they're going to have the same electronegativity. They're going to share those electrons evenly. Gasoline, well, gasoline's an oil product. Goodness, man. Till I just had my lunch. But gasoline is an oil product, so it's also it's non-polar. Now my last piece on this part is like dissolves like. So if I want to dissolve something that is non-polar, then what I need to use is I got to use a non-polar substance. So like if you get oil all over your hands, right? If you try and go in and use water to wash the oil off your hands, it's not going to come off. You're going to end up with a big old mess because water is going to turn out as polar and the oil that's on your hands is non-polar. So they will not be attracted to each other and you can't get it off. So what you got to use is you got to use something that's the same. And it's not great on your hands, but when I work on cars at home, once in a while, I'll use a little bit of gas, put some gas in a rag, and use that to get the oil off my hands. Now, why does the gas take the oil off my hands? Because the gasoline is non-polar. The oil on my hands from working on a car is non-polar, so they will attract to each other, and I can get the oil off my hands that way. So you got to use like substances to dissolve like substances. Excuse me. All right, now polar molecules. In polar molecules, the electrons are not shared equally. Okay, so let's see, we'll move over and do, where'd it go? There's black. So let's do H2O, which is water. So I'm doing this, I got oxygen, he's got 6. There's his 6. And then there's a hydrogen here, and there's a hydrogen here. All right. Now, if we look at the periodic table initially and look at electronegativities, right? Hydrogen's up here, and oxygen is way over here. Are their electronegativities going to be really, really close? No, they're pretty far away from each other. So therefore, they're going to have some really different electronegativities. So therefore, what we find is that the oxygen has a greater electronegativity than the hydrogen. So these little electrons, when they're shared, they're going to go around the oxygen, around it, and around it, and around it, around it, because he's got it. And he goes, oh, okay, you got it. Nope, I want it back. And he holds on to it and holds on to it and holds on to it. And they say, okay, you got it. Nope, I want it back. So who's got it more often? The oxygen has it more often. And because he has the negative electron more often, he ends up with a slight negative charge. Right? Now, what I just made up there is the lowercase Greek symbol delta, and it means slight. What it looks like, if I write it slow, it looks like a figure eight, but I didn't finish the figure eight, right? Because the figure eight, I finished it, go up all the way to here. Well, that's not a lowercase delta. And again, this means slight. So this means he has a slight negative charge in this end. Well, this hydrogen down here, he lost his electron, so he ends up with a slight positive charge. So we really end up with this molecule that's got a negative end and a positive end. That's similar to the Earth, because we have a negative end and a positive end called the North Pole and the South Pole. Right? So we end up with these poles on the end of the molecule of water. Because it's got poles, because it's got a negative and a positive end, we call it a polar molecule. This molecule over here didn't do that. They were being shared equally. All right? So there is no polarization of that molecule. All right, so what you do need to do is you need to draw this drawing in your notes at this point, because it said there we're going to talk about that in the lecture. So you will need to add that to your notes. So these guys have, in the rest of the notes there, it says not equal electronegativities. There's a partial charge is present, and it uses the Greek symbol, lowercase of delta, to represent partial charge. And I said I'll write this in the notes, so there's what that thing looks like. Right? And that's what I tried to draw up there, was the little symbol for delta. Letter E, this produces traits like surface tension in water as partial charges attracted to each other. Now, what does that mean? Is that if I took another water molecule and put him near this, he's going to actually, let me get rid of this, that positive end, that positive hydrogen is going to be attracted to that negative oxygen. Right? So there's this little attraction that occurs. And then we're also going to get another one over here that's also going to have an attraction. There's going to be an attraction between them. And then we'd have another one down here and another one over here. And we all of a sudden get this, and they start attracting to each other. And that's actually what causes surface tension. And what surface tension is, if you've ever noticed in a glass of water, if you fill a glass of water up all the way, you ever notice that the water actually does this? And it'll bubble up over the top and not fall off the edge. Or if you put a drop of water like you did in biology on a penny, notice that it actually bubbles up over the top of that penny. And it's all because those water molecules are all being attracted towards the center. Okay? They're being attracted because they're polar. That positive and negative charge is attracted towards each other. Okay? So again, you're going to want to write this in there in your notes, showing that whole idea of them being attracted to each other, polar molecules being attracted, causes things like surface tension. All right? And it's called actually hydrogen bonding is the actual real specific name for that. All right, well, I'm going to stop there for a minute. We're going to go on to part number 2 so we can finish this up. So I'll see you in a little bit at part number 2.